All right, so this question reads, mass, length, and time are all SI-based quantities. State two other SI-based quantities. So for a question like this, sorry, that was a little bit of a Hollywood alien debate that occurred in astronomy related to the Drake equation. Save that for another lesson. It's important to distinguish between units and quantities, right? So these are all quantities here. You say, well, mass measured in kilogram is the unit, length measured in meters is the unit, time measured in seconds is the unit. So we want quantities here. So let's just list them all for completion's sake. So we've got 1, 2, 3, and there are 7 total base units. So which ones are we missing here? We're missing current. We're missing luminous intensity. We're missing amount of substance. And we're missing temperature. 1, 2, 3, 4, 5, 6, 7. So that's all of them. Let's go through all of the base units. So we already said mass is kilograms, length is meters, time is seconds, current is amp, luminous intensity is the candela, amount of substance is the mole, and temperature is Kelvin. So pick your favorite out of this list of 4 here, right? You can't repeat any of these 3. And so I'll say temperature. And how about current? All right. Question goes on to say a wire hangs between 2 fixed points and a child's swing is made by connecting a car tire to the wire using a rope and a hook. The system is in equilibrium with the wire hanging at an angle of 17 degrees to the horizontal. The tension in the wire is 150 newtons. Assume that the rope and hook have negligible weight. Determine the weight of the tire. All right, so the weight of this tire, we're given a clue with sort of the tension in these wires here, because that's a force and this thing is in equilibrium. And so the downs have to equal the ups, the lefts have to equal the rights. And so we'll have to sort of resolve this tension vector and say, well, it's kind of moving up and to the right. So it has a to the right vector, which should equal this to the left vector, right? So because it's in equilibrium, this thing isn't moving or accelerating left or right. So the component of sort of tension this way balances the component of tension that way from this wire. So this one has an up component like that. This one has an up component like that. And because they're the same sort of, the hypotenuse is 150, the angle is 17. I think if that's 17, then this one right here is 17, right? That's some alternate interior angles or something like that. So I'll go ahead and label that. And if we can deduce what the vertical component of this tension is, and so I'll call it T sub V, the vertical component of tension, well, we'll double it, and then those ups have to equal the down weight, right? So sort of the up component of the tension here must equal the weight. So that kind of outlines our work for us. We've got this side that is opposite the 17-degree angle, and we know the hypotenuse is 150 newtons. And so if we think about the sine function, the sine of this angle relates the side opposite, the vertical component of tension, and then the hypotenuse, which is all of the tension, 150 newtons. And so now we can solve for the vertical component of tension by multiplying both sides of that by 150. The sine of 17 degrees is 0.29 times 150 newtons gives us 43.85 newtons, which means this component of tension over here, would be exactly the same calculation to show that it's 43.85. And so the key ideas with equilibrium is there's no net force, no net torque. And so the sum of the forces in the y direction have to equal 0. And we can already see that there are 43.85 plus another 43.85 acting up. So we'll double that. And so if there are 87.7 total newtons acting up, then that's how many we have to subtract away acting down to equal the net force of 0, which is sort of what equilibrium means, right? The sum of the forces adds up to 0. And so if that's my ups, then there's my downs, and that must be the weight of the tire, 87.7 newtons, right? The combined weight is sort of a V. A little bit of vector resolution, and then the ups equal the downs. So I like 87.7 newtons for that, but I'm going to kind of clean it up just a little bit more and call it 88 newtons. Final answer. Question goes on to read, the wire has a cross-sectional area of 7.5 millimeters squared and is made of metal of Young modulus 2.1 by 10 to the 11 Pascal. The wire obeys Hooke's law. Calculate for the wire the stress and then the strain. Okay. Young modulus, let's start with that. The Young modulus is equal to stress over strain. So we know the ratio of these two, but we don't know either one, right? We're going to have to calculate them. So let's expand these. Stress is force over area. Strain is the extension over the original length, right? They give us the cross-sectional area in millimeters squared, so that's given. We know that the force acting on, okay, the wire, let's read carefully. Is this not the rope, it's the wire, okay? With the wire hanging, okay, so it's a single wire, all right? Although we kind of treated it like two separate wires, right? Like, okay, this has 150 newtons sort of this way, this has 150 newtons that way. So we're dealing with the elongation in this. There might be a simplification that we could make here. Because it's kind of like, well, this 87 or 88 Newton tire is going to be a load sort of on each one of these, or should we just treat it like a single wire here? Let's think. I remember doing a similar question to this, and I think we could say, not really sure. Let's keep on thinking our way through it, because the force, you know, is going to be the load. So the 87 newtons of car tire divided by the cross-sectional area, that should be the stress. We calculate the strain by knowing the stress and knowing Young modulus. We should be able to deduce the strain sort of just from that. They don't tell us anything about the extension or the original length of it, so I'm not 100% certain that the correct force to use is the 88 we just calculated, but let's give it our best shot here and see how many marks we would earn here. So we're going to calculate stress, sigma, using force per area, and we'll say, is it as straightforward as the 88 newtons we just calculated? I kind of feel like that 88 newtons is divided between each sort of half of the wire. There's always something confusing about these, that's for sure. 7.5 by 10 to the negative 3, so millimeters. Wait a minute. If we had 7.5 millimeters squared, and we want to convert that into meters, so millimeters to meters, we've got to do that twice. So there's 1,000 millimeters per meter, and that would cancel out one of them, And so we got to be mindful of converting square units. We'd have to divide this by 1,000 and then divide it by 1,000 again to get square meters. A Pascal is a Newton per square meter. So if we take our 7.5 divided by 1,000, divided by 1,000 again, now we've got it in square meters. And so it should be 7.5 by 10 to the negative 6, right? And then it's meters squared. So we've got 88 divided by 7.5 by 10 to the negative 6. This gives me a stress of 1.2 times 10 to the 1, 2, 3, 4, 5, 6, 7 pascals. And then if we use this equation up here that says Young modulus equals stress over strain, then the strain would equal stress over Young modulus. And we just calculated the stress to be that, and the Young modulus is given as that. So we got our 1.2 by 10 to the 7. It's actually 1.173 repeating, so I still have that on my calculator. I just rounded it to report it to 2 significant digits. But I've got the full value in my calculator. I'm going to divide it by, open parentheses, 2.1 times 10 to the 11th, which gives an extension, which gives a strain of 5.6 by 10 to the negative 9. Oh, 5. All right. Now, possible that's correct, but it's also possible misinterpreted it somehow up here with this wire. Let's see what the mark scheme tells us about it. Ah, yes. The tension is what we should have used for that, not the load. Okay, so the tire, of course, right? It tells us what the tension is in each wire, and so we're dealing with the wire. And so we converted this right, but we used the 88 Newton force instead of the 150. So that was a mistake there, and so that would cost, a mark. And obviously this answer can't be correct because we plugged in the wrong number here, but the approach is correct. And so, yeah, 150 on the force, I should have thought more clearly through that. All right, so this has been another worked example with Dr. Schley. Not yet perfect, but that's okay. It's okay to make mistakes as long as we learn from them. We'll see you next time.